All right, let's start. Okay, so last time we discussed about this also normal set. So this is the last part of chapter 6.2, and this chapter is about also orthogonal set, right? So orthogonal set, yeah, just to help you remember what we learned last time. This orthogonal set is a set of set of vectors that are orthogonal to each other. So if it is composed maybe of these three vectors, then each of the two should be orthogonal to each other. Okay, and then now we talk about orthonormal set, and in this orthonormal set we add additional constraint or condition so that each vector length, the length of each vector in our vector set should be 1. Okay, so but once we obtain orthogonal set which are perpendicular to each other, and then it will be really easy to make this orthogonal set into orthonormal set because we just change the length without without distorting or changing the direction itself. So direction is preserved, and then if we just change the length, okay, so that the length is becomes 1, and then it can be easily orthonormal set from orthogonal set. Okay, and then yeah, last time we discussed a few properties about this orthonormal set. So first of all, orthonormal set and also orthogonal set, they should be a linearly independent set, right? So we talked, yeah, we discussed that, linearly independent set is much like also, yeah, orthogonal set is a much more strict condition than linearly independent. So if your set is orthogonal, and then they are automatically linearly independent, and so from that fact, you cannot have you cannot have a more number of vectors than the number of elements, because in that case, if we form that matrix, and then you will always find the free variable, which means these will be linearly independent, right? Okay, so in the case of orthogonal set or orthonormal set, it should be always this thin and tall matrix, okay? Or the square matrix, like a 4 by 4. Okay, and then this orthonormal set has an interesting property. Let's see. Yeah, also, yeah, interesting property of if as follows. If you just transpose this orthonormal matrix. Okay, so here, if you're given maybe 3 vectors, and then you form this matrix where each column is your orthonormal vector, and then you just transpose it, and then multiply it on the left. So U transpose U, if you form this, and then it will become always identity matrix. So, let's see. So in this case, it will be something like having 3 vectors on the left, because we transpose it, then we have 3 vectors as a column here. Then the resulting matrix will be, first of all, 3 by 3 matrix. 3 by 3 matrix. Then, interestingly, this matrix will be identical matrix. Okay. So here we will have all zeros for non-diagonal part. And this is because, so in this case, V1 transpose, yeah, let's call that as U1 transpose and U1. And so this guy will become U1 transpose U, right? But this guy will become, will be the same as the inner product with this guy and this guy. So U1 transpose and U2. So because they are orthogonal to each other, So inner product between them should be 0. So that's why we see all 1s along the diagonal, but 0s on the off diagonal. Okay, so this is quite an interesting property that we will use in the next few slides. But let me ask another question here. So what if we have just an orthogonal set, not orthonormal set? In this case, V1, V2, V3 in these two matrices are just orthogonal to each other, but their length is not necessarily 1. Okay, so their length can be 2 or 3 or minus, not minus, but 1 over 2 and so on. And then still in this case, we will have 3 by 3 matrix. And then what will be these two elements? So these elements will still be 0 because they are also the inner product between the different vector, but the orthogonal vectors are giving 0 inner product values between different vectors, and so still in this case the product between these two matrices of U transpose U will give U transpose U will give diagonal matrix. But what about these entries or these entries? So this entry will become U1 transpose U, and so this one will no longer be 1 because we didn't assume they have a unit length. So, but in this case still it can be represented as this. So it will be the squared length of each vector. Okay, so if it is maybe 3, 5, 7, it means the first vector length will be square root 3, okay, and square root 5 and square root 7. Okay, so now let's study about a few interesting properties of this orthonormal set. Okay, so suppose your matrix U is composed of an orthonormal column, just like these are 5 by 3 matrix, where we have 3 vectors that are orthogonal to each other, and the length of which is just 1. Okay, in this case we consider some vector x and y living in Rn, where n is 3-dimensional vector. Okay, so vector x is maybe 1, 2, minus 1, and y will be 2, 3, 1, for example. You just think of any of these 2 3-dimensional vectors. In this case, this theorem 7 says U times x, which means this U times 1, 2, minus 1. Okay. First of all, what will be the vector dimension of the resulting product of this matrix vector? R5, right? And then suppose that vector was 1, 2, 3, minus 2, minus 1, for example. Okay. So this is the result of product with this orthonormal matrix and this original vector. In this case, U times x, which is 1, 2, 3, minus 2, minus 1, the length of this vector is the same as 1, 2, minus 1. Okay, so this is the first item in this theorem 7. We will prove this shortly, but let's try to just understand the meaning of this equation. So, in the case of an orthonormal matrix, okay, orthonormal matrix is the matrix whose column is orthonormal vectors, and in this case, when multiplying this matrix with some vector, and then it doesn't change the length, although it changes the dimension of the entire vector. So it changes three-dimensional vector into five-dimensional vector, but overall the length of them should remain the same, which means 1 squared, 2 squared, minus 1 squared, and then taking the square root will be the same as 1 squared, 2 squared, 3 squared, plus minus 2 squared, minus 1 squared, and then taking the square root of them. Although this is not true because I just wrote a random vector, but this should be true when using the orthonormal matrix. Okay, then now we consider the two vectors in the three-dimensional space. Okay, so looking at the second one, and then we consider this two of these five-dimensional vector transformed by our matrix U. And then if we consider this inner product between these five-dimensional vector, and then that inner product will be the same as the inner product between the three-dimensional original vector. Okay, so this is the second theorem. So by combining this, the first item, the second item is saying that the angle between these two vectors are also preserved. So in the first case, in the first item, it is saying that the length is preserved, but yeah, so let's remember the formulation that we learned about this inner product. This inner product should be represented as this: the length of x and y and cosine theta, right? Between the two vectors x and y. And then this guy is like ux, uy, and cosine theta prime. So this theta prime is the angle between the new five-dimensional vector, ux and uy, and then this cosine theta is the original angle between these two vectors, right? So here, in this case, in the first item, we prove that, we understand that this guy and this guy should be the same, right? So this guy and this guy, the lengths didn't change, right? And then also this length and this length should be the same, which means if this is satisfied, and then the angle is not, the angle is also preserved. So length and angle are both preserved when using orthonormal matrix. Okay, then the third item is saying that if x and y and their inner product was 0, and then the inner product will be also 0 when they were transformed into five-dimensional vectors. Okay, so the third item is not new thing; it's just a special case of B, because if this was originally 0, and then the third item is saying this one should be also 0. Right? So the third one is nothing new. Okay, so let's prove this. So proofs. Oh, maybe it doesn't have any proof. Let me show how we prove that. Okay, so the first item is this, right? So each of them is a scalar, right? And then we can freely change this by just taking the square. Okay, and then let's see. Let's start with the left-hand side, and then we can do the trick of ux transpose ux, right? Okay, and then x transpose u transpose and u and x, right? And then u transpose times u is identity matrix, right? Because we proved it, right? Okay, and then in this case, it will become x transpose x, and so it will be the same as x transpose. The squared norm of an x. Okay, and then let's prove the second one. ux, uy, the inner product between them will be the same as the inner product between x and y. And so let's start from here, and then it can be represented as also ux transpose times ux. So this is not inner product, okay? So in this case, x transpose u transpose ux. And so, oops, sorry, this one should be y.
And x transpose u transpose uy.
Yeah, uy. Okay. Okay, so this part will become identity, and so x transpose y, and then it will become x inner product with y. Okay, so proof is really simple. Okay, and then now let's try to understand this more intuitively. So why doesn't the length of the vector change? Okay, why does the vector length remain the same? Okay, so let's think about the three vector case in our matrix U. So U is composed of these three vectors. Okay, also normal vectors U1, U2, and U3. And then let's consider the three-dimensional vector, maybe x1, x2, x3. So this is something like 1, 2, minus 1 or something. Okay, that we had in the last previous example. Okay, in this case, you guys know that this is this linear combination of the three vector. Okay. Okay. Then let's also represent this guy, or the original vector x1, x2, x3, as similar to this. So I'm going to change the representation of it in this manner. Okay, so it's quite obvious, right? And so let's compare this representation with this representation. Okay, and then you will easily see that this unit vector in three-dimensional case became this five-dimensional vector that are also normal to each other, right? So in this case, so if you remember something called the isomorphism. What was the isomorphism? So isomorphism was something like this. So in this three-dimensional space, we think of this hyperplane, which is a kind of a smaller, which has a smaller dimensions, and you just cut these thin plate and then move it to a new space, where the new space is exactly like just a two-dimensional space. Okay, x and y. Okay, so if we think about the inverse process or the opposite process, so you start with this some two-dimensional space, and then you move it to a new, you actually move it or embed it to a higher dimensional space. So this is what exactly is done in this case. So x1, x2, x3 are living originally in the three-dimensional space, and then this three-dimensional space was embedded into, for example, five-dimensional space where this u1, 2, 3 are living in. Okay, and then now u1, u2, u3 are having have the special property of being also normal, which means they are also perpendicular to each other, or orthogonal to each other, and then also the length of each vector is 1, right? And so let's think about this very special case of this standard unit vector. Okay, 1 0 0 0 1 0 and 0 0 1. So in this case, they are already orthonormal, right? They are already orthonormal. So this vector was mapped into u1, and then u1 was 1 2 minus 1 2 0. Then this one was 2 3 0 0 1, and then this guy was 1 2 0 0 5. Although they are not orthonormal vector because their length is already not 1, but let's just use this example. So suppose these three vectors are new orthonormal vectors in the 5-dimensional space, and then you are mapping these vectors, okay, and then those vectors still have the length of 1 between the old one and the new one. I mean, both the old vector and the new vector will have the length of 1, and then their angle also didn't change at all, because between these two they had a 90-degree angle, right? And then the new vectors will also have a 90 degree. So the new basis vector will also have a unit length and also the same angle between these basis vectors. Okay, then let's consider the other case where these three vectors are not orthonormal. So for example, their length is 1, but their angle is no longer 90 degrees. In this case, in this previous vector will have this nice property or nice shape of having a 90-degree angle, okay? And then, okay, let's think about just a 2-dimensional case, because we cannot go higher dimensional case. Let's think about this 2-dimensional case where the length is 1 and then the angle is 90 degrees. And then this vector and this vector is mapped into these 3-dimensional space, something like this, okay? Just a slanted thin hyperplane in this higher dimensional space, in the 3-dimensional space. And then now, if we think about this original two-dimensional space, where the universe was this 2-dimensional space, and then let's try to embed it into higher dimensional space, okay? In this case, so you guys kind of understand that those vectors living in this 2-dimensional space, this vector and this vector and this vector, and then these vectors will have a particular length and then some angles, right? And then we actually moved it and then embedded it into higher dimensional space. But still, those points, right, in these higher dimensional space, they will also have the same angle and length, okay? But what if we just break the rule of having a 90 degree? So in this case, we had a really nice 90-degree angle, which is nice property. But when embedding them, we actually slanted them, okay? We had the we decreased the angle, and that's when the vector had the angles between the vectors will no longer be no longer be preserved. Okay, so it's something like this. So yeah, keeping my fingers in mind. So this was like a 2-dimensional space. So we had these two vectors x and y. And then they have a certain angle, for example 30 degrees. And then now we are sending it into higher dimensional space, but now this vector became this vector, and then this vector became this vector, okay? And then suppose this guy was 2, 1, okay? And then this one will also have 1, 2, and 2, 1, right? and then this guy was 1, 2. Okay, and then this guy will have something like this. So this will become x and y, and so the angle is already decreased, right, from 30 degree to maybe 15 degree or so. So if the basis, I mean the angle between the bases are preserved, and then any angles between the different vectors will also be preserved, right? Okay, and then and then also in terms of the length, so also normal means they are having a 90 degree and then the length is still 1, right? But if we map this vector into the vector of length maybe 3, okay, and then from this length of 1 vector, the vector of length 1, it became the vector of length 3, and so the resulting vector of an x, okay, this vector, yeah, so suppose this vector was x, and then this was the mapped vector, and the length of this vector will become larger. Okay, so this is a little bit of a high level on and geometric understanding about this property. Okay, so yeah, you can just simply understand this theorem in this manner. So you originally have this really nice orthonormal basis vectors that are having 1, 0, 0, 0, 1, 0, and 0, 0, 1. And then without changing the angle between these vectors, and also without changing the length of these vectors, you are just embedding them as it is. I mean, without changing at all, you are just embedding it in a higher dimensional space where the vector length is still 1, and then also the angle between the vectors will still be 90 degrees. Okay, so you don't need to like warp or distort the spaces. Okay, by decreasing the angle or increasing the angle or stretching out the length and so on. So we don't need to involve this kind of operation, right? So we can embed this low dimensional space into higher dimensional space without changing anything. So this is the nice property of this also normal matrix. Okay, so so if you okay, any questions? Okay, then that's it for chapter 6.2. And then now the next chapter is about the orthogonal projections, and maybe half of them is what we already covered last time. So hopefully it should be quite easy to understand. Okay, so the first slide is saying, yeah, so the first slide is almost about almost all the contents. I mean, very summary of this chapter. Okay, so here's the situation. We are given some subspace W. Okay, and then some vector Y, and this vector may be inside of subspace W or outside of the subspace W. But let's just consider some general situation where Y is not in the subspace W. Okay, it's it's the situation that we often talked about. We have some plane of our subspace, and then we have some point, okay, or vector that are not inside of our plane because our plane is really thin. Okay, in this case, we already studied that Y can be decomposed into Y hat plus some vector Z, and here Y hat should be inside of our subspace, okay, and then Z is now inside of W perpendicular. Okay, so it's like we have a plane here as our subspace, and then some point y. Then this vector is decomposed into these two vectors, where this guy is called y hat, this guy is called z. Okay, then in this chapter, it's saying that this kind of decomposition of y being equal to y hat plus z, this decomposition is actually unique. Unique means given a particular y and also w, then this y hat will become a unique vector. So there will be only one unique y hat, or only one orthogonal projection, and also this z vector, which is this guy. We often call it as a residual vector, because we subtracted this y hat, or the component in our subspace W, from our original vector. So from our original vector, we subtracted its orthogonal projection component. Okay, and then this one is our z, and so this is considered as a residual vector, some remaining vector after subtracting the projection part. Okay, and so this y and y hat is unique vector. So there exists only one unique y and y. This z and y hat vector. Okay, that satisfies this condition. Okay, and so this one will be the main thing that we learned in this chapter. And let's formally state that, and that is this theorem 8. So theorem 8 says, suppose W is a subspace of an Rn, then you pick up one particular y, then y can be written uniquely in the form of this, where y is in W and z is in W hat, W perpendicular. And in fact, this y hat can be obtained or can be computed given this orthogonal basis of the subspace W. So suppose this subspace W had an orthogonal basis vectors from of U1 to UP, and then this y hat is having this form. Okay, so this is almost what we learned last time. Okay. And in terms of the notation, so let me look at the notation. The projection of y onto the subspace W, which is a y hat. Okay, so this is our subspace, and then this vector is our projected vector, orthogonally projected vector of y, and then that is written as this prose onto W of the vector y. Okay. Okay, then let's try to prove this theorem. So this theorem is saying mainly the two things. Okay, this theorem is mainly composed of two things. The first one is when decomposing y into y hat and z, where these two vectors are satisfying this, and then y hat will have this representation uniquely, right? And then also, again, this representation will be just unique. So there will be no other y hat or z. Okay? So this is the two part of this theorem 8. And let's try to prove that. So first, let's try to prove this guy. Y hat should be written as this one. And so these are almost what we learned last time. So let's think about y hat first, and then y hat should be belonging to our subspace W, and then if our the basis of our subspace was U1 through UP, and then we can represent C hat as this linear combinations of U vectors. Okay, and then now Z should be in W perpendicular. So we have to have y minus y hat, which is our Z. Okay, Z should be orthogonal to W, which means Z should be orthogonal to U1 and U2 and UP and U3 and so on, all the way until UP. Okay, then we plugged Z by this, and then this y hat is a linear combination of U1 through UP. Then we do this inner product with the U1, and then y and U1 will become the first term, and then from y hat, if we consider this inner product with the U1, and then the first term will survive, and so the first term will become like y times U1 minus C1 times U1 inner product U1. Okay, so this should be 0 because of this. So this inner product should be 0, and so here C1 should be U1 and y inner product with the U1. Okay, so that way we can compute C1 through CP. Okay, so that way we can see that this y hat is represented as this. I mean, as the linear combination of U1 through UP, where the linear combination coefficient is represented this. Okay, and then let's now try to prove this is a unique expression or representation. So the uniqueness part. So we now computed this representation as our y hat. And now the question is whether this y hat is unique or there exists some other vector that is different from this y hat. Still satisfying this condition. Okay, so the uniqueness is can be proved as follows. So suppose we have this decomposition where y hat is represented by this, okay, and then z part is just automatically determined by y minus y hat. Okay, z doesn't have any specific formula where we can obtain it. We just first obtain y hat and then just subtract it from y, and that will become your z vector. Okay, and then now let's think about another representation like this, where y hat 1, which is different from y hat, and that is still belong to W, and this C1 is y minus y hat 1. Okay, so here we set y1 hat, which is different from y hat, but still we are assuming that this vector is belonging to W, and this guy, which is a residual from this y hat, and this guy is belonging to W perpendicular. So this is our assumption. Okay, and then these two parts should be the original vector y. original vector y, and then let's move it to, let's just manipulate this equation into this form from this equation, right? And then now from this equation we can see that the left hand side, which is y minus y1 hat, so there is a typo here. It should be y hat minus y1 hat should be equal to z1 minus c. Okay, then this y hat minus y1 hat, each of y hat and y1 hat are belonging to w, right? And so we subtracted the two vectors where both of the vectors are picked up from our w, right? So since our subspace is closed under linear combination, so this guy is still belonging to w, right? So y1, y hat and y1 hat are both picked up from our w, and then we linearly combine them by just having this y hat minus y1 hat. That should still belong to our subspace w. And likewise, z1 minus z. So our assumption was z is belonging to this w perpendicular, and z1 also belongs to w perpendicular. So w perpendicular itself is another subspace. And so z1 minus z is also belong to our subspace w perpendicular. Okay. Okay, so the two vectors are the same. Okay, the two vectors are the same, but the first vector should belong to w perpendicular, and the second vector should belong to the first vector should belong to w, and then the second vector should belong to w perpendicular. But let's remember the definition of w perpendicular. W and w perpendicular. What was the relationship between them? You pick up any vector from one space and then another vector from the other space, and then you do the inner product, and then they always should be zero. The inner product should be zero because they don't overlap at all, right? So their intersection, okay, their intersection should be just origin is the origin only. There is no other vector. Okay, and so w perpendicular, by its definition itself, if we pick up one vector from w perpendicular, and that should be perpendicular to our original subspace. Okay, so it leads to this. Let's call this vector as a new vector v, which are the same vector, but v belongs to w and w perpendicular, and so v, the inner product between v from left side and the v from right hand side, they should be 0. Okay, so the same vector, the inner product between the same vector should be 0, which means that vector should be 0, and that is this v vector should be 0, which means y hat and y1 hat should be the same, and z1 and z should be also the same. So even though we started from the assumption that there exists some y1 hat which is different from y hat, but our conclusion was y1 hat and y hat should be the same. Okay, so that way we proved this uniqueness. Okay, so there is only one y hat and there is only one z vector given a particular y. Okay, so this is the uniqueness property of this orthogonal projection onto our subspace W. Okay, and Now let's move on to the next theorem of best approximation theorem. So this theorem is quite simple, but this one will be used oftentimes in the next two chapters. Okay, it's chapter 6.4 and 5. Okay, best approximation theorem. Best approximation theorem. Okay, so this theorem, I'll explain this theorem as follows. So you have Y and subspace W, and as we studied in the previous theorem, this Y will be decomposed into Y hat and Z, and this Y hat. Suppose this Y hat was this point, okay, and then by definition, this vector Z, which is our residual vector, is orthogonal to our subspace W, right? So that's why this Z belongs to W perpendicular. But in this case, this best approximation theorem is saying that let's think about the different situation. So you pick up one point just randomly from your subspace W. It could be this point, or it could be this point, or this point. So we may have this vector, this vector, this vector, and so on. Okay, amongst so many possibilities, okay, among so many vectors that you can pick up from the subspace W, this orthogonal projection of this vector Y is the best approximation of this Y, in a sense that Y minus Y hat, their length is minimum. Okay, so the minimum or the shortest. So in that sense, this Y hat, which is an orthogonal projection, is your best approximation of the original vector Y onto this subspace W. So best approximation. Let me explain this in more simple situation. So the situation is this. So you have this subspace spanned by this vector U1, and you have some vector Y here, and this vector Y is approximated. Okay, so you want to approximate this vector so that the approximated vector is belonging to your subspace. Okay, so you want to approximate this vector with or using some other vector that is inside of this subspace W. Okay, so in this case, this vector became this new vector, which is now inside of our subspace. And you can choose another vector. Maybe you can pick up this vector. Okay, and then in this case, this vector Y became this vector approximately. Okay, so this vector are all inside of subspace W, but they are now approximately representing this vector Y, the original vector Y. And which vector among all the vectors of subspace W, so which vector is the best approximation of the original vector Y? So how can we define the best approximation? The best approximation can be thought of as follows. So if we approximate this vector by using this vector, and then what is the remaining part? Or what is the error part? So the error part will be this vector, right? Because vector y, so suppose this guy was maybe z1 vector, and this guy is z2. Then in this case, y will be decomposed as z1 plus okay, let me change the notation. So let's call this vector as y1 and y2, and this guy will become y1 plus z1, where z1 is this. Okay, and then if we approximate y with the y2, and then the remaining part after subtracting y2 will become this vector. So this vector will become y2. So when approximating y with the y1 or y2, the remaining part will become z1 or z2. And which one is a better approximation? So the length of this vector is, if the length of this error vector is smaller than the other, then this y1 will be like a better or higher quality approximation of y vector, because simply the difference between original vector and the approximated vector, the difference was smaller. Okay, and then what is vector, for example, y star, which is such that this y minus y star, which is our residual, is minimum. Okay, so in this case we can represent it as this. This guy should be I'm trying to think about the notation. Okay, y dash. So this should be satisfied for all y prime. Okay, but here we have to still follow the condition that y star should belong to W and y dash should belong to W as well. Okay, so in this case we can call this y star as the best approximation that we picked up from our subspace W. Okay, so given the vector y, this y star is our best approximation from the subspace W, and that vector is actually the same as the orthogonal projection. So you just project this point orthogonally to our subspace W, and this orthogonal projection will become your best approximation in this sense, or based on this condition. Okay, so let's this is the theorem 9, which is called the best approximation theorem. So simply, if we have an orthogonal projection y hat, and then y minus y hat, which is our error vector, the length of this error vector is the minimum. Okay, should be the minimum, or it should be smaller than any other case or any other error vectors when using other v vector belonging to our subspace W. Okay, then let's prove this guy. Okay, so let's consider Y and the subspace W, and then this Y hat is your orthogonal projection onto this subspace. In this case, what is the error vector? That error vector is this vector, which is our residual vector Z. And this Z is has the smallest distance compared to other V, for example. So suppose you picked up another vector V from your subspace W. And then you can always think about this triangle. Where this is your Z and this is the difference vector from Y hat minus V, because you picked up this vector V different from a Y hat. And then we have this additional vector that is Y minus V, because this is Y and this is V. Okay, and then this triangle will become the one with the right angle, or the 90-degree angle. And where is the 90 degree? Where is the 90 degree? So the 90 degree will become here. So this one will become 90 degree. And why should it be 90 degree? Why should this angle be 90 degree? Okay, that is because this vector Z. So once you picked up a Y hat and Y minus Y hat, which is your residual vector Z, that will be belonging to W perpendicular, right? So W perpendicular, what was the meaning of it? So we have quite strict requirement for this W perpendicular. So this vector Z should be orthogonal to any vector you choose from this W, right? And now let's consider this vector, which is Y hat minus V. So that was this vector, right? And this vector is also a linear combination of the two vectors, where these two vectors are all belonging to W and also W, right? And so the linear combination of the two vectors from W will still belong to the same subspace, because it's closed under linear combination. Okay, so this Z vector should be perpendicular to this vector as well. So this Z is perpendicular to this difference vector between Y hat and additionally selected or different vector that you choose from subspace W. Okay, then if we bring this into we bring this into this new triangle when viewing it from the side. We look at this triangle from this angle. Okay, and then this one will have a 90 degree, and this one will have a vector Z, and then this one will become Y hat. So this one will become Y hat. This one is additionally chosen vector V, and this is what? This is Y minus V, which is the new residual. Okay, so you picked up V, and then the new residual will become Y minus V. This Y minus V, the length of this vector will be always greater than this vector, because it will always form the triangle with the 90 degree in this place. Okay, so from the Pythagorean theorem, the squared length of this guy and this guy will become the same as the squared length of the additional edges, right? And then in this case, the length of this vector should be larger than this, which means the length of an error when using a differently chosen vector v, and then the error will be always larger than the error vector or residual vector z, okay, when using the orthogonal projection. Okay. Okay, so so this is called best approximation theorem. It's quite, intuitively quite easy to understand, but there are many notations that are in these slides, like y hat and z and y1 and v and z1 and so on. But if you have like a geometric understanding about this, about these orthogonality, then it should be, I think it should be easy. Any questions so far? Okay, and then let's briefly look at the example. So suppose we are given this y, and then our subspace W that are spanned by U1 and U2. And then the problem here is to find the distance from y to the subspace, which is the length of vector z, right? And then we first compute y hat, which is the orthogonal projection. Then this orthogonal projection, by using the formula, we have this vector as an orthogonal projection. Then y minus y hat, which is our vector z, will become this vector. And then the error, or the length of this vector, will be computed as this, right? And so the square root of it, or the length of vector z, will be the same as this 3 square root of 5. Any questions so far? Okay, and then we now have 2 more slides. So, like the previous chapter, in the last part of the previous chapter, we discussed about the orthonormal vectors. So we do the same thing. We now consider some subspace W, but their basis is given as this orthonormal basis from U1 through UP. So now they are having a 90-degree angle, and then also the length of the vector will all be 1. Okay, so the length will be all 1, and then the angle will be 90 degrees. And in this case, still the problem is to obtain the orthogonal projection. So suppose y is this, and suppose this y u1 and u2 is your orthonormal basis vector for the subspace W. And then how can we compute this y hat? Okay, y hat. So in the case of orthonormal basis vector, we don't need to have this additional term. Right? Okay. So let's think about the simple case where we have this U1, which is the length of which has the length of 1. In this case, how did we obtain the orthogonal projection onto this line? So I'm doing the same derivation for it. Y minus y hat will be perpendicular to u1, right? And so y minus y hat, and this y hat should be alpha times u1. So y minus alpha times u1 times u1 should be 0, right? And so y times u1 will become alpha u1 times u1, and so this guy will be divided by, yeah, this one, yeah, will divide this left hand side, right? And so plugging this alpha here, we obtain y times, yeah, y inner product with the u1 and u1 inner product with u1 and u1, right? So this one will become your orthogonal projection. And now the length of the u1 is 1 because we assume also normal vector. And so we can safely remove this guy because this guy is the same as the squared norm of u1, which is 1. Okay, then let's understand this in a different manner. So suppose you have this line and this vector y, and we just think about this trigonometry or this shape of triangle, and what is the vector of this orthogonal projection? First of all, what is the length of this vector? What is the length? The length is the original length of y, the vector y, times cosine theta, where the theta is here. Okay? Okay, and then now I give you the vector of this direction, but the length of this vector is 1. Okay, so again, this vector is 1, the length of this vector is 1. And then how can we represent this orthogonal projection? This orthogonal projection, this vector will have the length of this, right? So this is the length, and this, yeah, this is not inner product. So we have the length, we have the direction, and we have the length, right? So this is our orthogonal projection. Okay, and what is this cosine theta then? Cosine theta. So let's use what we learned in the high school. Cosine theta is y times u1 and y times divided by the length of these two vectors. Okay? Okay, then now let's also change this u1, because u1 was assumed to be the having the unit length. But let's also change it as the vector whose length is not 1. And then how can we make this vector as length 1? So we can simply change it as this guy, right? So that way, even though the length of the vector is not 1, we can easily change that as the vector of length 1. Okay, and then from this equation, we have this formula for cosine theta. and again still this part, or oops, this part is giving the length, and this part is specifying the direction, where the direction vector has the length of 1, because we made this vector that way. Okay, and then we can cancel this out, right? We can cancel this out, and the remaining expression will become y times u1. I mean y inner product with the u1 and the length of u1, right? And so this part is the same as y times the length of y times cosine theta, right? And we have this unit vector, right? And then these parts will become the squared length of the unit vector. Squared length of the vector u1, and this guy will be u1 inner product with the u1. Okay. Okay, so I removed it here, but that's why we also, that's how we can also derive this kind of formula: u1 inner product with the u1 and y inner product with the u1. Okay, this times u1. Okay, we have the entire formula here. Okay, so this is another kind of derivation of this non-intuitive proof about this orthogonal projection. Okay, and let's go back to the slide where we only consider this orthonormal vector, the length of 1. The vector length is always 1. And in this case, this guy will be removed, right? And then y hat will be just simply y times u1 and u1. And from the perspective of length part, and I mean the vector length part and the direction part, what is the length and what is the direction? So this was the direction part. So this is the direction part, and this is the length part. So this guy is some scalar, and this guy is giving some vector pointing to some direction. Okay. And then now let's consider the basis vector of u1 and u2, having two bases, but both of them are also normal vectors. So in this case, y will become y inner product with the u1 and the direction part, and y inner product with the u2 and the direction part, right? So this one will become your orthogonal projection onto the subspace spanned by these two orthonormal basis vectors. Okay, then now we will do really clever trick. So this is an inner product, and this is just a scalar multiple. So this is a very thin dot. So this is a scalar, and this is a vector. And let's decompose this. So this is a scalar, but this is this inner product between y transpose, vector y and u1. And altogether, this will become really small scale. And we have this u1, right? Okay, and then can we change this? I mean, can we change the order between them by having the vector first and the scalar later. Yeah, in the next part. Okay, and then we can change it in the above equation as well. So this is this guy, and the entire part will become this y transpose and u1, right? And then suddenly we have, so we can switch the order, or we can change the order of computation. And then this guy will become, okay, so let me do another trick here. So we simply change the the two vectors involved in this inner product. And then this one will become u1 and u1 and yeah, u1 transpose and y, right? And so again, this part is the same as this part, and this part is the same as this part. Okay, and then in this case, we can change the order of computation so that we first compute this part, and later we have this vector. Then what is the size of this vector? It's similar to inner product, but it's called a outer product, where we have this really big matrix of u1 and u1 transpose. Instead of u1 transpose u1, we have u1 and u1 transpose, which will form this really big matrix. Okay, then we have a y vector here. Okay, so so time's up. So I will continue the remaining part, explaining the remaining part. But this kind of really nice trick is really the important part in this chapter. So please keep that in mind. Okay, and then next Tuesday we don't have a class, right? And then we will meet next Thursday. Okay, thank you very much.
교수님,
네.
지금 여기 공지 올려주신 거 보면 3-1을 3-2하고 6-1, 6-4까지 하신다고 하셨잖아요. 근데 이게 챕터 2 through 3-1, 3-2까지인가 아니면 그냥 진짜 3-1, 3-2하고 6-1
챕터 2는 우리가 시험을 한번 봤었죠.
첫 번째 시험 때 2-2.3인가 여기까지 하지 않나요?
내가 기억하기로는 아마 이 챕터의 마지막에 그 무슨 원투원이랑 원투 거기까지 시험 범위였고 그게 아마 이 단원의 마지막이었어요. 그러니까 아마 3장부터가 시험 범위인 걸 알고 있어요.
3장 3일, 3일, 6일부터 6사까지 이렇게
4단원을 안 하고 3단원, 5단원 5단원 저희가 다 썼고
5단원 자습하냐고요? 아니요, 5단원은 나중에 볼 거예요. 되게 중요한 부분인데 일단은 순서를 조금 바꿨어요.
저희가 3 배우고 6 배우고
그래서 시험 범위도 이제 비디오를 이제 보게 되면 비디오 3장을 커버를 하고 거기서 이제 내가 또 숙제를 내줄 거고요. 이야기 한 대로. 그 다음에 이제 6단 우리가 이제 배우고 있는
시험 범위가 5단원 안 해요.
보다
다다음 주 화요일 날이 시험을 보는 거죠. 우리는 3단원은 전체
3단원에 1장, 2장 3장이 무슨 크레이머 룰이라고 있는데 그거는 우리는 또 안 배워요.
3단원도 하고 지금 6단원에 1, 2, 3, 4까지
네.
2단원 저희 배웠던 그 부분은 그러면
그건 안 시험 범위 아니에요.
이어갔구나.
그러니까 기말고사는 전 범위가 다 커버가 될 거고요.
1단원
네.
문제요?
근데 이제 지금 우리가 보게 될 두 번째 중간고사는 3단원부터 3장에 1, 2 그리고 거기서 쓴 것처럼 그다음 우리가 6장 배웠으니까 이 다음에 6장 배웠으니까 6장에서 우리가 배우고 있는 부분이 시험 범위.
4, 5는
4장은 우리가 아예 안 배울 거고요. 5장은 6단원 이제 끝나고 배울 거예요. 네,
3장과 6장 일단 중간 테스트는 3장과 6장.
맞아요.
다음 주 화요일 날 수업이
없죠. 선거 날이니까. 네.
시험은 언제?
다음 주 말고요. 그 다음 주 화요일.
다 다음 주요?
네.
연기됐네요.
네.
아 대선 때문에.
그 공지 이메일 받았죠 아마?
아니요. 그 시험 연기됐다는 얘기는 못 들었고 홈워크 7 나왔다는 것만요.
그거 말고 내가 이메일 하나를 또 보냈을 거거든요.
아니 몇 시에 보내셨길래요?
그거보다 전에 보냈어요. 어제 밤.
이상하다. 스팸 필터 걸렸나?
아니면 그 블랙보드 웹사이트에 가면 거기 어나운스먼트에 가면 다 그 이메일로 보내진 그 공지들이 다 있을 거거든요.